Hey guys, this is Miss Bufford, and in this video, we're going to talk about the mole and molar mass. So your learning goals for this video are to be able to describe what a mole is in your own words, to be able to calculate the number of atoms, ions, or molecules in a sample, and to be able to convert between moles and grams. All right, so the first question that you might be wondering is, what is a mole? And contrary to what the picture at the beginning of this video showed you, it is not a fuzzy animal. But in chemistry, a mole represents a quantity of particles that is equal to 6.02 times 10 to the 23rd things. All right, so just like a dozen is equal to 12, a mole is equal to 6.02 times 10 to the 23rd items. And just to give you an idea of the massive scale of this number, if we take a look at all of the place values that we have to cover in order to get to 602 sextillion, that is the massive quantity. It's so large that it's really hard to comprehend. But we also call this number Avogadro's number. All right, and so let's talk a little bit more about moles. So why do chemists need moles? Well, having a unit that represents a large quantity of particles is useful for chemists because chemists deal with billions and billions of little particles at the same time. And it's a lot easier to say you have 1 mole of something than it is to try to describe the massive number of particles that you're dealing with. So we tend to kind of lump moles into these little packets or lump atoms into these little ideal packets called moles so that we can deal with those quantities a little bit easier. Also, being able to compare these quantities of one type of atom to another using numbers that are easy to deal with is useful for scientists because we have to oftentimes compare, the ratios of one type of atom to another in order to figure out a chemical formula or balance an equation. And so moles help make this easy by just scaling that to numbers that are easy to deal with. And you will also see over the course of this unit and the next one, which is going to be stoichiometry, that moles are kind of like the universal currency in chemistry. They allow us to compare quantities of different types of atoms in ways that we can't do with their masses or their atomic numbers. So moles are really, really important in chemistry. All right, so now I want to go ahead and talk about what molar mass is. So molar mass is the term that we use to describe the mass of 1 mole of any element or compound. And so that is, the mass of 6.02 times 10 to the 23rd particles of any compound or any element. So the units for molar mass that we're going to use are grams per mole. All right. And the mass of 1 mole of any element, if we're just talking about a single element on the periodic table, is going to be equal to that element's atomic mass expressed in grams instead of atomic mass units. All right, so let's take a look at some examples of that. Here's our periodic table. And in the past, last semester, we learned that these numbers right here, these are their atomic mass numbers. And if we're talking about individual atoms, then these are expressed in atomic mass units where we're counting up the number of protons and neutrons in the atom to come up with that mass number. And then, of course, the numbers on the periodic table take into account all of the different isotopes. But when we're dealing with larger quantities of these atoms and we want to express them in moles, then all we really need to do is change that unit of atomic mass units to grams, and that will tell you the mass of exactly 1 mole of those atoms. For example, if I was looking at nitrogen, the mass of 1 mole of nitrogen atoms is going to be 14.007 grams. Right? The mass of 1 mole of germanium atoms is going to be 72.64 grams. All right? The mass of 6.02 times 10 to the 23rd nickel atoms is going to be equal to 58.693 grams. All right? And similarly, if I have 207.2 grams of lead, that's going to be equal to 1 mole of lead, or 6.02 times 10 to the 23rd atoms of lead. All right, so these mass numbers, we can think about them as atomic masses. They still are atomic masses, but we're also going to be thinking about them as the molar mass for each element. Okay, these are also molar masses when they're expressed in units of grams per mole, because they tell you how many grams are in 1 mole of that substance. All right. So one other thing that I wanted to point out, because if we don't point this out, then it becomes a question that you guys have later. Some people will look at this and say, well, if I have equal atoms of hydrogen and beryllium, why is beryllium have a mass of 9.012 and hydrogen just have a mass of 1.008 grams? And the reason is because beryllium's atoms are larger. They have more subatomic particles in the nucleus, and they take up more space than hydrogen atoms. So not only are they going to be more massive, they're also going to take up more volume, right? So um, even though if we had 1 mole of hydrogen and 1 mole of beryllium, we have equal numbers of particles, but the beryllium atoms are larger, so they're going to have more mass and take up more volume. All right, so that is that. All right, so now we've talked about molar mass for single elements. All we have to do for that is just look at the periodic table, and we can easily find the molar mass for any element. But when it comes to calculating the mass for a compound, that just takes a little bit of a process. So the molar mass of a compound is calculated by adding up the masses of all of the atoms that make up one molecule of that compound. So let's take a look at our first example over here. I have some steps listed right here, but we're going to kind of walk through it as we go through some of these examples real quick. So sodium chloride is my first example. This is 1 unit of sodium chloride, and 1 unit of sodium chloride, the smallest recognizable unit, is going to have 1 atom of sodium and 1 atom of chlorine. All right, and so I'm going to go ahead and I'm going to list all of the elements that I have in this compound. So that's step number 1. I've listed my elements. Step number 2 is I'm going to go through and I'm going to count how many atoms I have of each in my chemical formula right here. All right, so I have 1 sodium atom and 1 chlorine atom. And then step 3 is I'm going to multiply the number of each type of atom by that element's molar mass from the periodic table. All right, and so the molar mass for sodium, if I take a look at my periodic table, is going to be 22.99. So I'm going to write that. And then the molar mass for chlorine, if I look at the periodic table, that is going to be 35.45. And I'm going to use that mass right here. And then I'm going to multiply the number of each type of atom by the molar mass, and I'm going to add those products together, and I will get my final molar mass. And so the molar mass for a unit of sodium chloride is going to be 58.44 grams per mole. All right. Before we go too much farther, for those of you who are taking chemistry from me, I wanted to go ahead and clarify a couple of rules that we're going to have about our periodic table this year. So for the rest of the year, anytime you need to pull a number off of a periodic table, a mass number to use in a calculation, you must always use this periodic table. All right. Although most periodic tables have, very the same masses. Some periodic tables will have slightly different numbers for their masses, and I want you to make sure that you're getting the exact same numbers that I'm using in my calculations so that your answers match mine. So we're always going to use this periodic table. And then rule number 2 is that anytime you pull a mass number off this periodic table, you have to round it to 2 decimal places. And that's just for the sake of being consistent across the board. I just want to make sure that all of you are using the same numbers as I'm using in my calculation, so we always end up with the same answer and the same number of significant digits in our final answer. All right, and so let's go ahead and just take a look at how to round a couple of these, because there are some that, a few that students make common mistakes on. And so let's just go ahead and take a look at an easy one real quick. We've got nitrogen here. Oops, here's nitrogen. And the molar mass for nitrogen is going to end up being, we'll zoom in here, 14.01. All right, so we need 2 decimal places. So I've got 1, 2, and that 7 tells me I have to round that 0 up to a 1. So this is going to be 14.01 grams. Oxygen, on the other hand, if you take a look at this, this is the only time it's going to be okay to serial round when you've got like 99999. And so this 9 is going to force this to round up, which is going to force this to round up, which is going to force this to round up. And so for oxygen, we're going to use 16.00 grams per mole for our molar mass here, and this should be per mole. And then fluorine would be the same. We would end up with 19.00 grams per mole here. All right, so there's those. Another one that tends to be kind of tricky, and I don't know if tricky is really the right word. I think sometimes students just, they want to move fast and they make rounding errors when they do this. But we've got sulfur right here, and sulfur is going to round to 32.07 grams per mole. All right, and now we're going to head over to the other side of the periodic table where there's some other things that students tend to make common errors on. We've got sodium here. Sodium is just going to remain 22.99 grams per mole. All right, potassium is a big one that people tend to make errors on, first couple times they do it. We get 39.10 grams per mole for potassium. And then let's see, we'll do chromium real quick. Chromium's another one where we're going to have to serial round if we just need 2 decimal places. So we end up with 52.00 grams per mole. All right. So remember, anytime you're pulling a mass off of the periodic table, you want to have 2 decimal places. In the case of lead, you can go ahead and add a 0 since that's already only got 1 decimal place. All right, so now that we've clarified how I want you to round these numbers, let's go ahead and go back to our lecture and we'll finish these examples real quick. So example number 2, I've got silver phosphate here, and step 1 is to go ahead and list out my elements. So I've got silver, phosphorus, and oxygen in this compound. Step number 2 is going to be to write how many atoms of each element there are in that compound. So if I take a look at my formula, I have 3 silver atoms, 1 phosphorus atom, and 4 oxygen atoms. And now I'm going to go ahead and multiply those numbers each by that element's molar mass from the periodic table. Remember, I rounded that to 2 decimal places. And I'm going to perform those calculations, and then I'm going to add up the products that I got, and that's going to give me 418.58 grams per mole as the molar mass for silver phosphate. All right, so let's take a look at this last example. I've got barium hydroxide. All right, so again, I'm just going to list out my elements. I've got barium, oxygen, and hydrogen. And then I'm going to count how many I have of each. So I've got 1 barium, 2 oxygen, 2 hydrogen, multiply by my molar mass from the periodic table, and then add the products all together to get my molar mass for barium hydroxide, which in this case is 171.35 grams per mole. All right, and so this little make a little chart tip here is a really good idea, especially when you're learning how to calculate molar mass. This is going to be a calculation that we do so much this year that it's going to become second nature to you, and you're not really going to always have to write this little chart out. But I do guarantee you that if you start out just trying to type in the numbers in your calculation or in your calculator, eventually you're going to make a mistake, and it's going to give you the wrong molar mass, and then the molar mass that you're calculating, and you're using in another calculation is going to throw off your other calculation. So just until you get the hang of doing molar mass, go ahead and make these little charts where we're listing out the elements, counting the atoms, multiplying by the molar mass, and then adding them together. It'll really help. All right, so let's go ahead and talk about how we're going to be using these molar masses and Avogadro's number. All right, so the goal here with these numbers is to be able to convert between mass and moles and the number of particles that we have. And so in order to do these conversions, I'm going to reintroduce you to our conversion factors that we talked about last semester in our math unit. So there are two conversion factors that we need to be familiar with here. There is this conversion factor utilizing Avogadro's number here. And so if we have this equivalence statement where we know 1 mole is equal to 6.02 times 10 to the 23rd particles, then I can take that equivalence statement and I can write these two conversion factors where I have 1 mole over 6.02 times 10 to the 23rd, or I can write that flipped upside down where I've got 6.02 times 10 to the 23rd over 1 mole. And now these are both equally valid statements, but depending on my calculation, I'm going to choose to use one over the other, depending on how I need my units to cancel out. All right. The second conversion factor we need to be familiar with here is using molar mass as a conversion factor. All right. So remember, molar mass is expressed in units of grams per mole. All right. And so I can write this as a conversion factor where I've got 1 mole over the molar mass in grams for an element or a compound. Or I can write the molar mass in grams for an element or a compound over 1 mole. And either of these are both going to be equal statements or equally valid statements, but I'm going to choose the one that's going to allow me to cancel out the units. And so now if you're looking at this and you're thinking, oh my gosh, I hate dimensional analysis. I remember that from last semester, and that was totally not fun. I have an easy way for you to do these calculations. So this flow chart right here will help you know where to put your numbers and what numbers you need to do and what step you need to do. All right, so basically what we've got here is we've got grams, moles, and particles. And if I'm starting with grams and I need to figure out how many moles that's going to be equal to, then all I need to do is follow this arrow and do what it tells me to do. So if I'm starting in grams and I need to get to moles, then I'm going to take that mass in grams that's given to me and I'm going to divide it by the molar mass, and that's going to tell me how many moles I have. On the other hand, if I start with grams and I need to know how many atoms I have, so this term right here, particles, is kind of a blanket term that could mean atoms, ions, or molecules, really just any tiny thing that you're counting, okay? And so if I need to go from grams all the way down here to particles, notice that there's not one arrow that goes directly from grams to particles, which means I'm going to first have to go to moles, and then I'm going to have to go from moles to particles. All right, so that's going to be a two-step calculation. So what we're going to do is I'm going to go ahead and do 3 examples for you. And these examples are going to be just like the calculations that you have in your practice packets. So let's go ahead and take a look at some of those. All right, so this first example calculation or example problem says how many atoms are in 2.3 grams of potassium? And so I think the easiest way to approach these problems is to go ahead and underline the information that's given to you in the problem. And then I always like to go ahead and draw an arrow back to what I'm trying to calculate, so what it's asking me to find. All right. And so I'm going to start my calculation with the information given to me in the problem. So I'm going to start with 2.3 grams of potassium. All right. And so if I'm starting here with grams, then I'm starting here on my flow chart. This is start. And if it's asking me to calculate atoms, atoms are particles, right? So that means I'm going to go all the way down here. This is where I want to end. That's my goal, okay? And so it's going to be a two-step calculation. So I'm going to go ahead and set this up for my next step. All right, I'm at grams. The first step is I need to get to moles. All right, and I have to divide by the molar mass in order to do that. And so if I'm dividing by the molar mass, then the molar mass is going to go in the denominator of this next fraction right here. All right, so, and I need the molar mass for the substance that I'm dealing with. And in this case, this problem is asking me about potassium. So I'm going to go to my periodic table and I want to look at potassium. So here's potassium right here. And I can see that the molar mass for potassium that I want to use is going to be 39.10 grams per mole. All right, so I'm going to write 39.10 grams per mole. I'm going to put moles on the top. All right, so because of this word divide here, that's why I chose to put 39.10 grams on the bottom. But notice how this is, in doing that, I'm already setting this up for grams to cancel out because I've got grams on the top over here, and now I've got grams on the bottom in the next fraction. So that's looking good so far, right? We got one more step. And so now I'm in moles. If I were to stop the calculation, it would tell me how many moles I have of potassium, but I want to know how many atoms. So I'm going to have to go one more step all the way over here to particles. And in order to perform that step, I'm going to have to multiply by Avogadro's number, right? And if it says multiply, then the number that I'm using is going to go in the numerator on top over here. So 6.02 times 10 to the 23rd atoms, because that's what it's asking about, over 1 mole. All right. And so this is the molar mass conversion factor right here. And this is that conversion factor with Avogadro's number that we just talked about on those previous slides. And just notice how using the words divide and multiply tells me where I need to put the number, so I don't actually have to worry about units, but it's always a good idea to pay attention to your units. So now I've got grams on top here and grams on bottom, so that's going to cancel out. Moles on top here, moles on bottom, so that's going to cancel out. And I'm going to end up with units of atoms, which is perfect. All right, so now if I plug this into my calculator, I'm going to go ahead and write this out in the order that it needs to be typed into your calculator so you know exactly how to type it in. So I would type in 2.3 divided by 39.10 multiplied by 6.02 E23. And remember that when we're using the calculator and scientific notation, using that E function just is much better than having to remember where the parentheses need to go, because sometimes these calculations, they get a little complicated when we're trying to enter a bunch of numbers into our calculator at once. So if you just use the E function, then your calculator automatically knows that that is going to be a number in scientific notation. All right, so let's go ahead and plug that in. I've got 2.3 divided by 39.1 multiplied by 6.02 E23, and I get my calculator answer of 3.541, and that's good enough, times 10 to the 22nd atoms of potassium. All right, so there's my calculator answer, but I need to make sure that my answer is going to be expressed in the correct number of significant digits. And so if I take a look at the numbers involved in my calculation here, I'm multiplying and dividing. So my answer needs to match the same number of significant digits as the number that had the fewest. And we're going to ignore Avogadro's number when we're determining sig figs for this. Normally, if this was the real world, we would take that into consideration. But for right now, we're just going to take a look at our other measured values. So I've got my molar mass here that has 4 significant digits, and I've got the number I started with that has 2. So my final answer can only have 2 significant digits. And remember that when our numbers are in scientific notation, it's only the coefficients that contain our significant digits. And so I'm going to look at my coefficient. I'm going to say 1, 2. And since this is a 4 right here, I'm not going to round up. So my final answer is going to be 3.5 times 10 to the 22nd atoms of potassium. All right, so there we go with this one. This is our final answer here. All right, so let's go ahead and take a look at another example. All right, for this example, it says, what is the mass in grams of 3 times 10 to the 19th molecules of sodium chloride? All right, so I'm going to underline what's given to me. I've got 3 times 10 to the 19th molecules of sodium chloride, and it's asking me to find the mass in grams. Okay, so I'm going to start with the number that it gives me, so 3 times 10 to the 19th molecules of sodium chloride. All right. So if I'm starting with molecules, that means particles right here on my flow chart. That's where I'm going to start. And it's asking me to find the mass in grams, and so this is my end point. All right, so now I need to go the opposite direction down this chart. So for particles, I'm going to have to convert to moles first, and in order to do that, I have to divide by 6.02 times 10 to the 23rd. And if I'm dividing by that number, I'm putting it down below. So 6.02 times 10 to the 23rd molecules of sodium chloride. All right, over 1 mole. Okay, so this is a two-step problem. So now I'm here at moles. I need to get all the way to grams, and so now I'm going to go to grams, and now it's telling me I need to multiply by the molar mass. So here we go. I need to multiply by my molar mass, but I need the molar mass for sodium chloride. All right, and so there are going to be times when you're in the middle of a calculation and you realize you need the molar mass for something, so you're going to have to kind of go off to the side and do a little bit of side calculation and then use the number you get. So let's go ahead and do our side calculation here for calculating the molar mass of sodium chloride. I've got 1 sodium atom in that formula and 1 chlorine atom. And I know the molar mass for sodium, if I look at the periodic table, is going to be 22.99 grams per mole. 22.99. And the molar mass for chlorine, if I take a look at my periodic table, it's all the way down at this end, is going to be 35.45. If I round it to the correct number of decimal places, so 35.45. And so I'm going to do the math, grams per mole. This is 35.45 grams per mole. And then I just add these together and I get 58.44 grams per mole. So there is my molar mass here, and I want to plug that in up here in my calculation. And it says that I need to multiply by the molar mass, and so my number is going to go on top. So multiply goes on top. Grams per mole. All right, I'm just going to put my little equal sign there. Now I need to plug this into my calculator, and I'm just going to go ahead again and just write out how I'm going to type this into my calculator. So I'm going to type 3E19 divided by 6.02E23, and then I'm going to multiply that by that molar mass of 58.44. All right, so let's go ahead and do that really quick. 3E19 divided by 6.02E23, and then multiply by 58.44. And all right, my calculator answer is 0.00291, and that's going to be molecules of sodium chloride. All right, now I need to make sure that my answer is expressed in the correct number of significant digits. So this has 4 significant digits, and this one has 1. So I need to have 1 in my final answer. So that's going to be equal to 0.003. So remember, I start counting from my first non-zero digit. So there's my first one right there. And this 9 tells me that I have to round that 2 up. All right, molecules of NaCl. So there is my final answer for this problem. All right, so the ones where we've got to go all the way from grams to particles or particles all the way to grams, those are going to be our longer problems because they're the two-step problems. But more often in this class and in reality, we're just going to mainly be converting between grams and moles. Being able to calculate the number of particles in a sample is not as practical as being able to convert between grams and moles. This is a calculation that is going to be an everyday calculation for us for a while. And it's an everyday calculation for a regular chemist. So let's go ahead and take a look at this example. How many moles are there in 56 grams of aluminum? All right, so again, I'm just going to go ahead and approach this by underlining the information that's given to me, and then I'm going to draw an arrow back to what it's asking me to find. Okay, so it's asking me to find moles. And so here I'm going to start with 56 grams of aluminum. All right, and I need to convert that to moles. And so I'm going to follow the arrow all the way over to moles, and that's telling me I need to divide by the molar mass. So molar mass meaning the molar mass for aluminum. And so I'm going to need to go to my periodic table, and I'm going to need to find aluminum. And I can see that my molar mass for aluminum is going to be 26.98. So I need to divide by that. So I'm going to put that in my denominator. So 26.98 grams per 1 mole of aluminum. All right, and that's it. That's all I have to do because now grams will cancel out and I'm left with units of moles, and that's what I was asked to find. So in my calculator, I'm just going to take 56 and I'm going to divide it by 26.98, and that is going to equal, here's my calculator answer, 2.056 moles of aluminum, but I need the correct number of significant digits for my answer. I've got 4 here and 2 here, so my answer has to have 2 sig figs. So 1, 2, and then this 5 tells me I need to round that 0 up, so I end up with 2.1 moles of aluminum. And there we go. There's my final answer. So you can see that these one single step problems are a little bit easier. And this is definitely a skill that we're going to need for the rest of the year. So you want to make sure you're really good at these calculations. Thank you for watching Buffered Chemistry. Subscribe to my YouTube channel for more chemistry help.